So good morning, everybody. It's a pleasure to present at this meeting, and I'd like to thank the organizers for inviting me. So the topic is trying to discuss what we can do in NLP today beyond the very common and often kind of the default end-to-end approach, and specifically I'll refer to multi-text summarization. So generally speaking, in supervised machine learning in general, and just, do you see also my cursor? Moni, can you see my cursor?
Yes.
Yeah, okay. Generally, in supervised learning, right, we have some data for our task, examples of the input and the output for the task. And by default, we train an end-to-end model. And this end-to-end approach became also very popular with the advance of recent deep learning models that are very powerful and enable us to address more complex tasks in an end-to-end manner. But still, there are complex tasks out there. Multi-document summarization, about which I'll talk in a minute, is an example. We're just giving the full task, just letting models be trained from directly generating the output directly from the input, ends up being too hard also for today's models. And then a decomposition-based approach is taken. And in this case, basically, we would naturally decompose the task to several of its natural subtasks and try to train modules, specific modules for the individual subtasks, which are easier, and you also get better control this way. Of course, the key aspect or key requirement for enabling such a decomposed approach is to have data sets for the intermediate input-outputs, right? Because usually when we get training data for a task, we only have the input-output of the main task, and we don't have data for the intermediate steps. But then if we manage to create some data sets representing input-output of training data for intermediate steps, we could take the main task input as input for the first subtask model, and this output of the subtask as training data, and just train a model for this subtask, and so on for the second subtask, and so on. Of course, the question is, where would we get this data? And I'll get to that question with respect to MDS. So now in this talk, I'd like to take the multi-document summarization MDS use case, where the input is a cluster of related documents about some topic, and the output is a summary. And the dataset simply consists of many such pairs of input topic and output summary. And when it's approached with end-to-end in the end-to-end manner, people train encoder-decoder or seek-to-seek models that learn to take as input a large collection of text and generate the output summary. And in summarization, if we go to the case of summarization, the task does consist of natural subtasks that people were aware of, and these may include salience. So taking the input document cluster, you may first want to decide which pieces of information in these documents is salient. These are the highlighted here in yellow. And then once you identified all the relevant or the important pieces of information, you'd like to cluster them, because in multi-document summarization, the same information might appear here, and you don't want to repeat it. So you'd like to cluster all the source segments that convey roughly the same meaning into a cluster. So in this case, all the red spans roughly convey the same information, all the orange spans the same, and so on. So effectively, you kind of give different colors on the source text to the salient spans on the source text, which can also be viewed as like taking a cluster of the red spans, the orange spans, and so on. And once you've identified that all these pieces of information, let's say all the red spans are roughly similar, you'd like to fuse them into a coherent sentence that will go into the output summary. So that's kind of a natural decomposition approach for multi-document summarization. And of course, as I said, it requires getting such training data for salient spans, for clusters, and so on, which are not available in the original just input-output. You just have text and the eventual summary. So this brings me to the outline. I'll first describe a work that discusses how can we obtain such training data for the intermediate steps. Then I'll talk a couple minutes about ProCluster, actual system that follows this approach and indeed achieves better results. And finally, I'll talk about a separate contribution that is utilized in the MDS setting, in the multi-document setting, which is a generic cross-document language model. So let me start with the first work on how can we get training data for intermediate tasks. And this was work at Cornell. It was one of the 2 best paper runner-ups. And it's collaboration with Mohit Bansal's group at UNC. So as we said, this is the decomposition that's a classic decomposition scheme, and how would we get the intermediate data? And the key idea here is to try and use alignment of information between summary and source documents. So let me elaborate on this. A major contribution in this work was the proposal that when we look at the, let's say, if we look at these, let's say, colored spans, each of them is supposed to capture a piece of information, we would like to look at these spans at the level of propositions, rather than look at complete sentences, like in this example sentences. We can realize that sentences often combine different facts. Each of them is called a proposition, let's say a predicate, a verb, and its arguments. Like here, that Prime Minister wanted talks to be in Cambodia. Opposition leaders, I'm now talking about the green one, wanted them abroad, and the opposition leaders in other facts said that they were fearing arrest at home. So we see that actually this sentence, single sentence, includes 3 facts, we call them propositions, and we would like to decompose the information to the kind of atomic proposition stated in each sentence. But then when we look at these propositions, if the summary includes this proposition, it must come from somewhere in the source documents. And we see that both in source A and in source B, this fact that Hun Sen wanted the talks to be in Cambodia is mentioned. So it means that it should be possible to align each proposition in a summary with a source sentence proposition. And this can give us training data for proposition alignment. And indeed, and just schematically, I'll describe this with the color scheme. That's what I'll use next. So imagine each colored span is a single proposition, and same span means aligned or paraphrastic propositions. And using such data, I won't get into the details, you can look at the paper, we create a generic tool that can take candidate propositions and decide whether they should be aligned, whether they're paraphrastic or not. We call it SuperPal, it's available at Hugging Face. So now using this tool, SuperPal, the proposition alignment tool, we can now take the source cluster of source documents and the summary and align the pieces of information. So we decompose the summary to all its propositions and find the alignment. So if we have the red here, we also see that it appears here, also in the second documents and so on, okay? So using the tool, we can create this, if you like, color, we can make this coloring of the documents. Notice, of course, that in the source, many pieces are not colored because it's non-salient information that didn't find its way into the summary. So that's what we can manage with the SuperPal tool. Now, once we have such alignments over a large data set that we process automatically with SuperPal, we can start creating our data sets. So if we look at all the source segments of all colors that were aligned, so all the colored segments in the source, this actually gives us training data for a salience model, right? Everything here is salient because it ended up in the summary. So all of these can be colored, highlighted in yellow, and being a salience data set. So now we can take a model that gets the source documents as input and needs to produce these highlighted segments as output. Next, we would like to cluster those with the same color, but we can do that because if we see here some highlighted spans, we can track back their colors and cluster them back, because all the spans here that were aligned with the same summary span, it's meaning that they are paraphrastic because they all mean the same as the same summary span. So now we can create a data set, a gold data for clustering model. And finally, we also know that let's say that the red, that the first sentence, for instance, was created from the green and red clusters. So now we can train a model that takes these two as input and needs to predict the summary sentence, the corresponding summary sentence as output, and so on and so forth. So this way we can actually derive automatically from available input-output data sets data for all the intermediate tasks. And this, I would like to mention, it's not a slide, the work we did a couple of years ago, step by step, they did something similar with respect to data to text generation. So often it's the case that given just the input output of the main task, it is possible to derive training data for subtasks. Okay? So having this training data, we developed ProCluster, which is a full-blown, a complete summarization, multi-document summarization system that follows this line, again, with our UNC partners. So just to go very briefly, I go very quickly over this, but we extract propositions, then we using salience data, we train a salience model. Then we apply clustering, we can fine-tune the clustering model, we add another step of ranking, and then finally, after ranking, we take the top-ranked clusters, in this example, let's say 1, 2, 3, and fuse the input sentences from which, the output sentences, sorry, from which we create a summary. So as you can see, we could develop a complete decomposed approach that's with trained components relying on the derived data that we created. And you can see here some examples. These are salient sentences clustered to topics. Here you can see how the sentences were fused in cluster F to a summary sentence, taking parts from 2 sentences and so on and so forth. And indeed, the results of these systems substantially improved the state-of-the-art results on the more challenging types of data sets available in the community. I just mentioned that improving around 2 rouge points in summarization is a very substantial improvement. Finally, now, so this, I would say, finally, before wrapping up the entire talk, I would like to tell a little bit about a parallel effort that is complementary to the MDS work and also is leveraged by the MDS work. Our work on multi-document summarization is part of a broader line of research on multi-document processing. We're trying to promote this direction in NLP. And this is work with our partners from AI2 Seattle. And this is about when you want to apply, to develop some models, like the salience models, for instance, that we develop, a concrete model that performs a task or a subtask over multiple documents, maybe just using a model like BERT, or let's say BART, if you need a seek-to-seek, is not good enough, and you'd like to have a model that is tailored specifically for the multi-document setting. So let me talk about CDLM, cross-document language modeling, right? So typical language models are just trained on single text. If you want to apply them on multiple texts, we'd like to train them on multiple texts. Single models trained on single text end up capturing information about internal text structures. In cross-document setting, often we need to know about cross-text relationships, like which pieces are paraphrastic, which elements co-refer. And accordingly, language model pre-trained on single text we would expect them to be useful for single text application, but in the multi-text scenario, we would like language models that were also pre-trained for the multi-document setting. To do that, we take clusters of related documents, like those we've seen in the example of MDS. And the key trick here is to do what we call cross-document masking. So technically, we simply feed a set of related documents into a long sequence, into a long-range language model. We specifically use long former. And now the masking is such that you might, that you might mask a word, let's say, in a single document, but the model can, at a training time, can look not recover the masked word just from this document on its own, but also from other documents. So think for a minute for this word talks in the example we had before, that the Prime Minister wanted the talks to be abroad, in Cambodia. And imagine that we mask the word talks. A regular language model would have to figure out that it's about talks just by looking at the same document. But the way we pre-train with cross-document masking allows our model to kind of peek at the other documents that do mention, let's say, that the Prime Minister wanted discussions or negotiations to be in Cambodia. This would encourage the model to learn to align between overlapping pieces in different documents and be able to encode not just within document relations, but also cross-document relations. So that's the trick. This trick works very well when we tested it on multiple cross-document tasks, especially co-reference. We got very nice improvements. We also did ablations that show that indeed training on related documents makes a difference. If you just train on random cluster of documents or single documents, it works much less. And also some attention analysis shows that indeed the model attends much better than other models to co-referring information. Like here, nominates and name actually refer to the same event, and our model puts this attention top in the attention list compared to other models. So just to wrap up about the cross-document language model, it's the first general language model for cross-document downstream task. It's available. And as a next step, you would like to develop, we're working to develop a similar approach for encoder-decoder setting. So just concluding the entire talk, I mainly wanted to tell about an approach for decomposing complex tasks to subtasks when we need better performance over simpler tasks or better control. And the key trick here is how to solve in your own derived data for intermediate tasks. And at the end, I talked more broadly about the multi-document setting and suggested we need targeted models that are pre-trained for the multi-document setting to model cross-document relations. That's it. Thank you for listening, and I'm happy to take a couple of questions.
Thank you, Ido, for the talk. And let's switch to some questions from the audience. First of all, can the entire model can be trained jointly, end-to-end, in an end-to-end matter, or is it inherent that you are looking for this task decomposition that you have outlined?
So I think the key point is to see how, instead of just modeling everything end-to-end, trusting, the internals of, let's say, the transformer to properly model all the subtasks that do involve, right? Also, when you do end-to-end, eventually the model internally does have to model salience, and identifying redundant information has to fuse this information into an end sentence. So the key point is to try and decompose, and this way give the model more data to understand, bring your own domain knowledge, understanding that these subtasks need to be addressed. Now, in ProCluster that I presented, each subtask was trained separately and optimized separately. In kind of flavor of complex deep learning systems, it could be an interesting research direction to try and maybe train all of them together, maybe in some multitask way, and try to have more global optimization. It's going to be very challenging, but I think that's maybe a way to bridge, to bring together decomposition and end-to-end into a unified scheme while still helping the models by breaking tasks into simpler subtasks.
Thank you. And which cross-document relations are you able to capture?
So that's actually a good and open question, because just like we don't know exactly, in the single document setting, there has been, after transformers kind of, deep language models came out, there was a line of works that tried to investigate and showing that they capture certain syntactic information and semantic information and co-reference relations. So there is some understanding, not that great actually, also for the single. We don't really know which information is truly encoded there, but we have some hints. I think it's going to be interesting to do something similar to for the cross-document setting. This attention analysis that we performed suggested that the model does manage to map internally cross-document co-reference, like that nominates a name in one document refers to the same event as name in the other document, or that Obama and President cross-documents refer to the same thing. Mm-hmm. But I think there's more work to understand what are really the important kind of informational cross-document relations that we want models to capture. And maybe if we understand that better, we can develop better kind of pre-training schemes, better masking strategies, better strategies to drive our models to capture the important cross-document relations.
And how does the training set created? Is it vulnerable to the order of the documents? Can you avoid biases? Can you make it, can you identify irrelevant documents and so on?
Yeah, I think I mean, all these questions refer to also additional cases. Maybe when you don't just take your data, but you also derive additional data sets from your data, maybe they get a bit amplified. So I agree. I mean, we haven't addressed these issues too much yet. I mean, I think it's a fair question, but overall, we found that when you derive such, let's say, silver data, because you derive it automatically, it's still, the quality is good. So if you have smart ways to derive data, I'm again pointing at this step-by-step paper from 2019, I mean, where we derived the ways for text planning, again, smart ways. So it takes some smart thinking, but it is often possible to derive this intermediate data at high quality.
Regarding that, one person from the audience asked if the code is available and you can send a link to the code or to the paper or to any relevant resources.
Yes, I think everything. This is this is a question one likes to get, right? And actually, like for CDLM, we have by now hundreds of downloads. I mean, people can. We do have it. I mean, you can look at if you look at my DBLP or Google Scholar. I mean, there are these papers. The last one has an archive version, and there are links. And if you don't find, just write me. We'll be happy to give the links.
Thank you. One last question. Can you elaborate on the way you score your summarization? Is it the usual way you score summarization?
Yeah, here. Yeah, I mean, yeah, here. Yeah, I mean, in the summarization, yeah. Here. Yeah, I mean, these are just the rouge. So this is rouge 1, rouge 2. This is RSU. I mean, the variant of rouge. So yeah, we use the same metrics. We also did, I mean, in the paper, we also have manual evaluations. So for instance, it's mentioned for lack of time, but it turns out also that human subjects also liked our sentences, our few sentences, to be more coherent. And it's also possible because an end-to-end system has to fuse the output sentence from the whole source text. We only have to fuse an output sentence from a small cluster. So apparently it succeeded to fuse. We used BART for the text fusion.
For the text fusion.
Cluster as input, but only the cluster as input and the output sentence as output, and it did better coherence. So from that perspective, we just use the standard text summarization evaluations, both automatic and